Solving logarithmic equations is what we're going to look at today. So remember the property of equality. If the log of A equals the log of B, and you have to have the same base, then A would have to be equal to B. And remember that um, we can't take the log of a negative number or 0. And you always want to check for extraneous solutions. And remember, extraneous solutions mean false solutions, solutions that when you plug them back into the original equation, they do not work. So looking at the first one, we have a log of 2 equals a log of 2. So that means we can set the arguments equal to each other. Remember, the argument's just what you're taking the log of. So 4x is equal to 20 divided by 4, and x is equal to 5. So then we want to check your work, and we get um, the log of 2 of 4 times 5 has to be equal to the log base 2 of 20. And so the log base 2 of 20 equals log base 2 of 20. So that's easy. So that one checks out. Looking at question 2, sorry, and that means my answer is x equals 5. So looking at question 2, same thing. We have log base 10 equals log base 10. Remember, it's 10 when it's not written. So 2x minus 7 has to be equal to x plus 6. And so that means we want to combine our like terms. So subtract the x, and I get x minus 7 equals 6. Add the 7, and x is equal to 13. And then, of course, check your work. So the log of 2 times 13 minus 7 has to be equal to the log of 13 plus 6. So this is the log of 2 times 13 minus 7 is 19, and that equals the log of 13 plus 6 is also 19, so that checks out. And the last one, same thing. Log of 7 equals log of 7, so set the arguments equal to each other and solve. So when we do that, add the 13, add the 10, 17 is equal to 17x divided by 17, and x is equal to 1. So then we want to check our work. So to check my work, I'm going to plug it back in. So we have the log of 7 minus 13 times 1. It has to be equal to the log base 7 of 4 times 1 minus 10. So when I do that, this ends up giving me the log of base 7 of negative 6. And that has to be equal to the log base 7 of, again, negative 6. So they're equal to each other. However, if you look right here, remember we can't take the log of a negative number. So what does that mean? That means that this is extraneous, and there are no solutions. So there's another way we could have looked at this problem to know that there was going to be no solutions from looking at our answer, and that would be to actually find the domain of our logarithmic function. So we looked at finding the domain graphically. So how would we find the domain algebraically? Well, just like for when we did square root functions and found the domain, you had to take what was underneath the radical and set it greater than or equal to 0. It's the same concept except for we don't write greater than or equal to 0, it's just greater than 0 because again we can't take the log of 0. So I'm going to do that first for the left side here because that's one with the x. So if I find the domain of the left side, then that means the domain, because that's the one with the x, 4x has to be greater than 0, divided by 4, so x is greater than 0. So the domain is of this equation is 0 to infinity. 5 fits within that domain, so that's why it was okay to use that for our answer. Same thing down here. We want to look at both sides because both sides have the variable x in them for question 2. So here we would take 2x minus 7 has to be greater than 0. So 2x has to be greater than 7. So x has to be greater than 7 halves. And over here, um, x plus 6 has to be greater than 0. So x has to be greater than negative 6. And so when you have 2, you want to always take the larger value that you have. So I know that since 7 halves is 3.5, I would use that for my domain of this entire function. So the domain would be 7 halves to infinity. And so 7 halves is again 3.5, and 13 is bigger than that. Therefore, it is in the solution set that we have. Looking at question 3, we can do the same thing. So 7 minus 13x has to be greater than 0. So then subtract the 7, divide by negative 13. Remember, when you divide both sides of an inequality by negative value, you flip the inequality sign. And then we're going to do the same thing for the other side. So this was 4x minus 10 has to be greater than 0. Add the 10, divide by 4. And of course, we can reduce that into 5 halves. Before this, if we were to make a number line, you would see that 7/13 is here. It's about 0.5, and 5 halves would be over here, so 2.5. We have numbers greater than that, which goes this way, and numbers less than this go this way. So that means that these two graphs, if you were to graph them, would not overlap each other. Therefore, this is not in the domain because one would be in here in between these two values. And so therefore, that's why it's extraneous, because the domain is from negative infinity to 7/13, parenthesis, union, parenthesis, 5 halves to infinity. And so even if we looked at the graph of this, I went ahead and plugged that into my y equals with the the base button on our calculator. But again, we don't want to usually use this to graph because we're going to do it by hand. But just to show you, if I were to graph both these functions, you can see that the two don't overlap. There is no intersection. So there's no place where they're going to be equal to each other because that's what you're looking for. And so therefore, that is why there's no solution. So just another way to look at it rather than plugging in and check your work. But you can do either way, just kind of a preference. So solving by rewriting in exponential form is the next part we're going to look at. So recall that the log of base b, so log base b of a equals e. If I want to rewrite this in exponential form, that would be the base stays the base, so b, sorry, I wrote 5 of b. So b to the e power equals a would be rewritten. And if I want to solve by rewriting exponential form, you want to isolate the log expression first. And so when you are solving these problems, to rewrite it, after you isolate the log expression, you're going to rewrite in exponential form. And you can only have, so only do this when there is one log in the equation. So you can't rewrite this in exponential form if there's multiple logs. That's why we did the properties of logarithms in the last section. So we went from an expanded form to condensed form and vice versa. So if you have multiple logs, you need to use those properties to write it into one single log first, and then you can rewrite it. So looking at this first one, this is already isolated. There's nothing on the outside of the log being added or subtracted, and there's only one log in the equation, so we can rewrite this in our exponential form. So 2 to the power 5 equals 4x. 2 to the fifth is 32, and divide by 4, and so we get x is equal to 8. And then, of course, don't forget to check your work. If I plug 8 into here, it checks out. We can also, remember, look at the domain to check. So for the domain, for x has to be greater than 0. So x has to be greater than 0. So we're looking at 0 to infinity, which 8 is in that domain. So it checks out. So you can either check it out by plugging it in or by using the domain. Let's go ahead and look at this one over here. So here we need to isolate the log expression first. So it's not isolated yet. So I can take this 2 and do a property and bring it up as an exponent, or I can divide it out. I'm going to go ahead and divide it out because usually that's easier. So I'm going to divide both sides by 2. I get the log base 3 of 12x minus 3 equals 4. Now, sometimes I have students that will ask me, why did I not divide what was inside the log? You can't divide what's inside there because that 2 is being multiplied by this whole expression, and again, it's inside the log. Now that I have the log isolated, I can go ahead and put this in exponential form. So 3 to the power 4 equals the argument 12x minus 3. 3 to the power 4 is 81. Add the 3. 84 equals 12x. Divide by 12. And you get x is equal to 7. And of course you want to check your work. So you can plug the 7 in to check, or you can use the domain to help you. So if I look at the domain, I'm looking at what I'm taking the log of. It has to be greater than 0. So 12x minus 3 has to be greater than 0. So 12x has to be greater than 3. Divide by 12. X has to be greater than 3 twelfths, which we know we can reduce because 3 goes into 3 and 3 goes into 12. 1/4. And so x has to be greater than 1/4 for the domain. So 1/4 to infinity. This is in the domain, therefore it checks out. Looking at the next one, we have log base 2 of 2x plus log base 2 of x equals 7. So for this one, notice that there are 2 logs in the equation. It's not isolated as a single log expression. So this is where we use our properties. So we want to isolate the log first. So that is step 1. So when I isolate the log, if I have 2 logs being added, we remember the property that states if there's 2 logs being added, we multiply the arguments. So we have 2x times x, which is actually 2x squared, which we'll rewrite in just a second. So log base 2 of 2x squared equals 7. Now that the log is isolated, I can go ahead and rewrite this in exponential form. So 2 to the power of 7 equals 2x squared. 2 to the 7th power is 128. Divide by 2. And we get 64 is equal to x squared. So how do I solve for something that is squared? Remember, you can take the square root of both sides. And when you do that, don't forget to write the plus or minus. So we get x is equal to plus or minus the square root of 64 is 8. And then, of course, you want to make sure to check your answers. So if we look at the domain of this right here, 2x has to be greater than 0, so x has to be greater than 0 over here, and here x has to be greater than 0. So the domain is from 0 to infinity, which means that the negative answer would not work. So the only answer is x equals 8. Of course, you could always check this by plugging your value back in. So if we look at this with our calculator, you would even see that if I do math log base 2 of 2 times 8 plus, and then math log base 2 of 8, enter, you get 7. But when I plug in a negative value, instead, notice it's going to say error non-real answer, so it's not in the solution or in the domain. That's why it says that. And so that's just another way to check your work. So again, you can plug it in or you can look at the domain. I like to look at the domain because I think it's faster, but it's just, again, a personal preference, whatever works for you. Looking at the next one, again, we need to isolate the log first. So to isolate the log first, we would use our properties of logarithms. I have 2 logs being added, so I can condense this by using multiplication. And then you distribute. Now I can go ahead and rewrite this in exponential form. So 3 squared equals x squared plus 8x. 3 squared is 9. Now remember, if you have a quadratic term, a linear term, and a constant term, in order to solve this problem, you must set it equal to 0. So I'm going to take that 9 and subtract it to the other side. So we get 0 equals x squared plus 8x minus 9. And how do you solve a quadratic equation? You can use the quadratic formula or you can factor. Factoring's a lot faster if you know how to do it and it works. So do we have factors of -9 that add up to 8? Yes, we do. They would be x plus 9 and x minus 1 because 9 times -1 is -9 and 9 minus 1 is 8. So this would be our factorization and then you would solve by setting each one of these binomial equal to 0 because if what is inside of here is equal to 0, 0 times this is 0, and if inside of here is 0, then 0 times this is 0. So 0 equals x plus 9 and 0 equals x minus 1. Subtract the 9, we get -9 equals x. Add the 1. And so now I want to check both my answers. So again, you can check it by plugging them in and using your calculator to help you, or we can check them by looking at our domain. So I'm going to go ahead and do that. So if I look at my domain, here x has to be greater than 0. Here x plus 8 has to be greater than 0. So that means x has to be greater than -8. So the larger value that we have is 0. So that means we are going to use that for our domain. So -9, that means is extraneous. So this solution does not work. And 1 is bigger than 0, so therefore this solution does work. Again, you can plug it into your calculator to check as well if you want to. We're just going to go ahead to the next one. Looking at question number 8. So this is already isolated. The base is not written, so remember that means this is base 10. So we can go ahead and rewrite this in exponential form. So this is 10 to the power of 5 is equal to 3x plus 1. So 10 to the 5th is 100,000 equals 3x plus 1. Subtract the 1. And then divide by 3. So 33,333 is equal to x. If I check my answer by looking at my domain, 3x plus 1 has to be greater than 0. So 3x has to be greater than -1, so x has to be greater than -1/3, so -1/3 to infinity. This is in that domain, therefore this checks out. And again, you could plug that in to check your work. Looking at question number 9, again, the base is not written, so we know this is a base 10. It's already isolated for the log, so 10 to the -1 equals 7 minus 2x. For this, you can write that as a decimal if you want, or we can think about this. If it's 10 to the -1, we know that's 1/10. Whatever works for you is fine. And then we want to combine our like terms, so add the 7. I need a common denominator to add fractions together. So this would be multiplying the 7 by 10 over 10. So if I do my work off to the side here, that gives me 1/10, because remember to add fractions you need common denominator. 7 times 10 would be 70 over 10, because that's really equal to 7. So that gives me 70 plus 1, 71 over 10. And then I'm going to divide both sides by -2. So if I divide by -2, remember to divide a fraction, you multiply the reciprocal, so I'm going to do the work over here. So 71 over 10, the reciprocal of -2 over 1 is times -1/2. So multiply multiply fractions straight across, numerator times numerator. So 71 over denominator times denominator, -20. And so that would be our answer. And we can use our calculator. So -71 divided by 20, notice is -3.55. I'm going to leave my answer in fraction form though, but just so you know, -3.55, if that helps you to look at the domain. So if I look at my domain here again, I can use what's inside of here. So for the domain, 7 minus 2x has to be greater than 0. So subtract the 7, -2x has to be greater than -7, divide by -2, which means we're dividing both sides of the inequality by negative. So flip your inequality sign. -7 divided by -2 would be +7/2. So x has to be less than 7/2. And so, of course, this is less than 7/2, so it works for a solution, so it checks out. And let's go back up here for a second. I just noticed that I accidentally added the 7 instead of subtracting. So that should have been -7, which means this would be minus, this would be minus, and change this one over here. Sorry about that. So -69 over 10 times -1/2 give us, for our solution, and then for this one, same thing. That gives us 3.45, which, of course, if you look back at your domain, we have to make sure that this is less than that 7/2, which we know if we do 7 divided by 2, that gives us 3.5. So this is less than that, so that checks out. So x is equal to that. So sorry about that, and make sure you fix that, which makes sense because what I had before, you have to have x values less than 7/2, which is, of course, 3.5. Okay, so moving back to the next problem, number 10. So looking here, notice that the logs, there's 2 of them, and we have that 3 in front. So for this problem, you can't just divide the 3 out. If you do, you'd have to divide each term by 3, which means that this would have a 3 underneath of it. So the easier thing to do here would be to bring that up as an exponent. And so this would be the log of x cubed minus the log of 2 equals 5. Now I can go ahead and if I have two logs being subtracted, I can use my properties and divide the arguments. So this would be x cubed over 2 equals 5. Remember, this is base 10 when it's not written. Now that this is isolated, I can go ahead and rewrite this in exponential form. 10 to the 5th is equal to x cubed over 2. 10 to the 5th is 100,000 equals x cubed over 2. We want to get rid of this 2 because remember you do PEMDAS backwards, so multiply both sides by 2. So 200,000 equals x cubed. How do you get rid of that cube? You take the cube root of both sides. And when you're taking the cube root, you don't do plus or minus. It's only for even powers that you're getting rid of. And so for this one, we just go ahead and write the decimal that we get from our calculator. So x is equal to the cube root of 200,000, which is equal to about 58.48. And then of course you want to check the domain. So you always look at the domain of the original problem before you move that 3. So the domain, our x value is greater than 0, so 0 to infinity. So this fits within the domain, so therefore that's my solution. Why don't you go ahead and do number 11 on your own. When you're done, you can unpause the video to check your work. So for this problem here, let's go ahead and look at this. We have 3 logs, and we need to write this as a single log. They're all being added. That means we're going to multiply each of the arguments and put it into one log. Now that that's happened, we can simplify our numerical expression. And actually, no, I just realized that this doesn't even have an x in it. I think I was missing, so we need to fix this. This should have been the log base 2 of 4x, so fix that. So let's put an x there, because otherwise we're not solving for anything. So this is 2 times 3 times 4x, which is 24x. And so this would be 2 to the power of 3. Now I can write it in exponential form, equals 24x. 8 equals 24x. Divide by 24. And x is equal to 1/3. And so then for this problem, of course, you want to check your work. So the domain of this, if I have 4x here, it has to be greater than 0. So domain's 0 to infinity. So this fits within that domain, so it checks out. And that's it for solving our logarithmic expression. So just to go back, remember if it's a log equals a log, you can set the arguments equal to each other and solve. So that was on the first page here. So log equals log. And if not, then you can isolate the logs and rewrite it in exponential form, and always make sure to check your answer, because remember we can't take the log of 0 or a negative value, and so if that happens then it's an extraneous solution. So always check to make sure it's in the domain, or plug it back into the original problem and check your answer that way.